Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation FETs, physics perspective. This is lecture number 22 and the topic of the lecture is spice model equations. So, we will start from where we have left in the previous lecture. Now, let us look at the device capacitance model in level 1, and the value of gate to source voltage is given as 2 by 3 W into L into C aux, where C aux is basically the value of the oxide capacitance per unit area, right. Now, if you look at this minus W times C aux, this will be in the saturation region which you will get, and in the triode region it is given by this quantity here. Now, if you look very carefully, it effectively means that in saturation and in the triode region, the charge sharing between source and drain varies, right. And as you can see, the source side gets more and more charged during the saturation region, and in the triode region it is relatively less, as you can see. Now, the reason why this value of this abruptly change takes place. However, the problem with these equations are that though they are okay to solve very easily, but you will see an abrupt change in the equation from saturation to the triode region, and therefore maintaining a continuity of the gate to source voltage during the transition is a difficult task. And therefore, in order to do that, a modified expression was found out and was given by this expression here, and this is given by this, and then it was told that CGB was approximately equals to 0, because in deep inversion, because of the screening effect, the gate to bulk potential will be approximately equals to 0. If you look at the saturation and in the triode region, you still have the square law being coming into picture, right. The square law is still there. So, VGS minus VTH is basically the overdrive voltage, right, and that gives you the effective value of the W this thing. Now, if you look very carefully, so let me take the second equation, because that's, let me write down this equation, and I will write down VGS minus VTH whole square when this becomes equals to 2 times VGS minus VTH minus VDS, right, whole square. When this is true, then what we get is that you will get this to be equals to 1, this whole quantity will be 1, 1 minus 1 will be 0, and this whole quantity will get removed, right. If you want that this equation should come back to this equation, then we effectively say that this quantity is very large as compared to this quantity. So, I can say that this quantity is relatively very large as compared to this quantity, right. Once this is true, then denominator becomes very large, and therefore, this become approximately equals to 0, and therefore, this reaches to this same equation as you see in the top. If I do change in its idea, then the overall thing which we get from out of it is that the overdrive should be as large as possible in order to sustain this equation in a proper fashion, and CGB should be equals to 0. Now, this was for the gate to source capacitance only. Now, if you want to model the threshold voltage in level 1 for VSB less than 0, which means if you have a negative VSB, then it is given as VTH equals to V built in plus gamma times phi root phi plus 1 by 2 VSB by root phi as the overall value of the threshold voltage. And when VSB is greater than 0, then we write this to be as gamma VSB root phi, right. And therefore, as the VSB value goes on increasing more and more, source to bulk, you will see that this quantity increases, the second quantity starts to increase in the second term, which means that this value goes on increasing, primarily meaning that your threshold voltage will go on increasing, which means that if your source to bulk potential is increasing, right. So, VSB is what? VSB is given as V source minus V bulk. If this quantity goes on increasing, it can only happen when the bulk VB goes down, right, and Vs is kept constant. Generally, we do not touch source potential to the larger extent. If we therefore reduce the V, if we go on reducing the value of VB, VSB increases and threshold voltage also increases. Now, if you look at the V built in is basically given as KT by Q ln of NA by Ni square, and it depends therefore on the doping concentration. This is to a larger extent fixed value which we get, and so we do not get any change in the value here. So, I get VTH is equals to V built in plus gamma times phi plus VSB to the power 1 by 2. The built in potential is given by this expression here, as you can see on the right hand side, and we can write down therefore VTH is equals to VT0 minus gamma times root phi. This is the modified equation which we get, assuming that V built in is relatively very small, we get this, and therefore we get VT0 minus gamma root phi. We get gamma is the body factor which is there, gamma is defined as the body factor. Higher the value, more is the effect of VSB on the threshold voltage, and phi is the potential which you see here. What is VT0? VT0 is basically the zero bias threshold voltage for a large device. So, we are all assuming that the gradual channel approximation, and therefore, my channel lengths are very large or relatively very large. Now, if the device is operating at the edge of the saturation, then the level 1 model does what is that it assumes that VGS minus VTH equals to VTH. Remember, what was the condition for this thing? This was the condition, right? And therefore, at the edge where the saturation is the starting, I will obviously get this expression, that VDS, right. So, if you look at VDS, it will be basically VDS will be approximately equals to VGS minus VTH, correct. And therefore, if you appropriate change, I will get VGS minus VDS is equals to VTH, and that is what you are getting here. And you will get CGS to be equals to this much and CGD to be equals to this much, W times Cox. Cox is basically is charge capacitance per unit area which you will get, right. Therefore, the capacitance value goes on changing as you move from one region to another, from saturation to linear and so on and so forth. Now, let us come to level 2 model, and this is also known as a Grooves-Froment model. So, level 2 model takes into account a large number of higher order effects, right. And these large number of higher order effects will be inbuilt within the device structure. Here we are again assuming that constant threshold voltage has been taken care of, it is only a function of the VSB, source to bulk voltage, which we are assuming. However, this dependency on VSB about the threshold voltage is not correct for very long channel devices, because the charge in the depletion region will also vary according to the local voltage. How do you define a local voltage? Local voltage is basically defined as the voltage at that particular point within the channel. As you can see from here, that as the x value goes right from this point to this point, so local potential goes on increasing as you move. This will be V built in, and this will be V built in plus VDS1 in this case. If source is grounded, it will be V built in, and this will be V built in plus VDS1, which you will get here. Then we write ID to be equals to 1 by 2 mu Cox W by L VGS minus VTH0. VTH0 is the threshold voltage at 0 bias into VDS minus VDS square by 2. Up till this much point, if you remember, all of you, that this was the nonlinear part of the ID. What has added here is this second quantity, this and this, right. And this gives you the variation of the current because of VBS. You will ask me how this happens, because if your VBS varies or VSB varies, the amount of charge in the inversion layer will go on changing, and therefore, to carry the same amount of current, you possibly require a larger or smaller gate voltage, threshold voltage changes. When threshold voltage changes, the saturation current will also change, because you remember it is VGS minus VTH whole square. So, if the threshold voltage lowers down, you will get a larger current for the same amount of gate voltage, right. And therefore, if you see the last statement here or the last expression here more carefully, then it depends, it is basically depending on the value of VDS here and a parabolic dependence of VDS here, right. It also depends upon VBS here and VBS here, which is about to source potential variation you will get. If you look at this expression, looks complicated, not only complicated, but it captures the effect of VBS on IDS, which was missing in other expressions, and that is the reason this is relatively more accurate as compared to level 1. If you take ID gamma factor, which is gamma is basically the body coefficient factor, then ID will also depend upon the value of gamma. If you look very carefully here, this gamma factor is coming somewhere here, right, and therefore, as the gamma factor changes or it becomes more and more, the current actually starts to drop down for the same value of VBS and VGS, right. And typically, If you take VDS to be very small, then the whole equation which we have pointed out in the previous slide actually boils down to level 1 model, right, and for therefore it predicts a value of current which is not slightly less than the square law current which was predicted by level 1. The edge of the saturation region is given by VDS sat and is given as VGS minus VTH 0 minus phi f plus some quantity here. This we have already known, we have studied during our basic device physics, but this is sort of a correction factor which comes into picture, correction factor, and it depends upon many factors, all these factors are there. So, you see, if you take this expression and you assume that this quantity is 0. So, if I say 2 by gamma square into VGS minus VTH 0, right, plus phi of f, if this quantity is exactly equals to 0, then I will tell you what happens. In this case, then what will happen is basically this will be 0, and therefore, you will be left with the fact that VDS sat saturation will be just equals to VGS minus VTH 0 minus phi f, that will be the value. So, you see, this cannot be equals to 0. So, what I am left is that VGS minus VTH 0 must, if this becomes equals to minus phi f actually, then you will have this quantity, which means that VGS minus VTH 0 is what? Is the overdrive voltage with 0 base to source voltage. When VBS equals to 0, at that point of time the threshold voltage available is given as VTH 0. So, VGS minus VTH 0 is basically the overdrive voltage which you see. If that happens to be equal to this phi f value, which is the potential available to us, negative of that, then we end up having the same equation as we know from level 1 analytical model, right, and gives me, and so this equation or this expression explicitly tells me that my VDS sat, the saturation value of the drain to source voltage, is actually dependent on the value of gamma as well, right, provided this quantity, which quantity, this quantity does not hold good, it does not hold good. So, this is there, and now in the saturation current, therefore, I can write down ID is equals to IDS sat multiplied by 1 upon 1 minus lambda times VDS. As you can see now, if lambda would have been 0, that means there is no CLM, then in that case this will be 0 and you will have ID equals to ID sat, at which place when lambda equals to 0, which means if in the absence of a channel length modulation effect or when there is no CLM, then say that the drain current is exactly the same as my saturated drain current, which means something like this. So, when you get this like this is my ID sat and my ID is this one. So, all my values are exactly the same and therefore, I can say ID equals to ID sat when lambda equals to 0, which means that I am not taking any second order effect. However, if you take some second order effect, you see as lambda goes on increasing, this quantity will go on increasing, 1 minus this quantity will go on decreasing and this quantity will go on increasing, and that is what the channel length modulation effect is like this. So, it goes on increasing with the value of VDS, because as the value of VDS increases, this goes on increasing. In level 2, lambda is not specified, right, and it is obtained by calculating the width of the depletion region between the pinch off point and the edge of the drain. So, the idea is that if you are able to get the point where the drain will actually pinch off somewhere here, then you will see that this distance you subtract from this distance and that will be the effective channel length, and that is the reason we write down W by L minus L depletion, 2L depletion, because on both the sides source and drain you will have, right. Now, using a simple PN junction diode theory, I can show delta L to be equal to this quantity where VDS sat is basically the pinch off voltage which we see. The model should be continuous across all the regions, right. So, we need to ensure that the absolute value of the drain current and its derivative both are continuous at the edge of the region, but it is not, right. So, one way to remove it is that to find out delta L from this expression which is shown here, this expression which is shown here, where Vi times lambda. So, there will be a lambda also here, Vi times lambda is given by this basic quantity here. Now, let me come to another problem statement of level 1 and level 2, which is very, very important, is that the mobility degradation with the vertical electric field in the channel is there. What does it effectively mean? It means that as the vertical electric field in this direction goes on increasing, since you are pulling larger and larger amount of charge carriers near the silicon dioxide interface, the mobility of the charge carriers will degrade because there will be effectively large amount of scattering taking place. And if you look at this expression here, mu 0 is basically my low field mobility, and there is a correction term which is being introduced in the level model, which takes care of the reduced mobility because of the large electric field available to us, where ut is basically a fitting parameter between 0 and 0.5, and my ue is again an empirical formula of 0.15, right, and uc is basically my gate to channel electric field, which is basically uc, or even you can write as ec. So, this is the transverse direction electric field which you encounter. So, higher the value of uc, right, higher the value of uc which you will get, higher electric field will actually tend to make this whole thing go down, right. Now, if you look at for example, the threshold voltage here, if the threshold voltage value goes on increasing, then VGS minus VTH will go on decreasing, right, and therefore, also your mobility will also tend to increase. So, higher threshold voltage entails a higher mobility in a sense, right, and that gives you a good idea about the mobility degradation model. Subthreshold model is implemented in level 2 model, and it is defined as V on, and it is given as VTH plus gamma times VT, where VTH is already the threshold voltage of the device, and gamma is given by this factor which you see in front of you, right, and these Cox is the oxide capacitance. However, NFS is basically an empirical constant. You fit the value of empirical constant such that you get a particular gamma, for you get a particular value of V on. Once you get this particular value of V on, you feed it into this expression and get the value of drain to source current, right. What is ion? Ion is basically drain current when you are calculating at a very large strong inversion region, correct, and therefore, this gamma is basically sort of a fitting parameter which comes into picture. Interestingly, subthreshold behavior, as you can expect, is basically an exponential behavior. So, amount of gate voltages you are giving, out of which some voltage is used to create the channel, which is equals to VTH, and some of it is being used to draw the charge carriers away and from the depletion region, that will give you the value of IDS, and ion is the drain current which you see in this case. Now, level 2 model therefore represents two short channel phenomena, right. One is the threshold voltage with length, which is basically known as roll off, threshold voltage roll off, and another is velocity saturation. What is velocity saturation? Velocity saturation is when your channel lengths are relatively short, if you plot voltage versus velocity of the charge carriers versus electric field, then you will see the graph comes something like this, which means that first of all velocity increases linearly, and then it starts to saturate at very high values of electric field, right. So, the mobility is basically defined as V by E, velocity per unit electric field, and therefore, you will see that this is almost constant mobility at low electric field, but the mobility tends to decrease and become almost at very high electric field, your change in the velocity is almost 0, and therefore, I would expect to see my mobility fall down to a very low value at very high electric field. Now, there is a problem, you can see the problem statement here, that in level 2 model there is a kink in the drain current, right, at VTH, and this is because of the discontinuity of the current flowing through the body. Now, let us come to the last model, which is basically the level 3 model, and it has got an improved accuracy, and it can work as small as 1 micrometer long channel, and it is given by the expression shown here, and these are empirical constants which we have already discussed, and the mobility degradation value gives me this particular value, that it is mu effective upon 1 plus mu effective by into VDS upon LL, which you see here, and therefore, both vertical and horizontal electric fields are considered. So, it is basically 2-dimensional dependency of mobility degradation when your channel lengths are very short, approximately 1 micron thick, and this is the value of mu effective which you see, where mu 0 is the low field mobility and VGS minus VTH is the overdrive voltage. Now, the drain current for level 3 is given by this expression, and it is equals to mu L times Cox into W effective by L effective, multiply this whole quantity here. And what we do is that we will just plug the value of VD sat here whenever we want to convert from a linear region to a saturated region. So, if you look very carefully, level 2 and 3 are both based on slight analytical, which is derived from level 1, but we are also introducing certain empirical values, sort of curve fitting values. So, they are realistically correct to the experimental values available to us. Now, disadvantage of level 3 is of course discontinuity, which is there as level 2, and there is a large error in the output impedance of level 3, and level 3 also has the same threshold voltage, sub threshold current as level 2, but there is a discontinuity in strong inversion region. So, major problem of level 3 as compared to level 2 is a strong discontinuity and the error in the output impedance of the device. Let extension of BSIM series, if you look, what has happened is, as the scaling of the devices goes on increasing, as you reduce the dimension of the device, it is becoming more and more difficult physically to have more accurate and computationally efficient at the same time equation. So, BSIM adopted a different approach, and they used numerical empirical parameters were added to simplify the equations. And in that generation, people used BSIM 1, BSIM 2, BSIM 3, next generation model for micron and deep submicron devices. Let me come to the last model which is there, and this is known as EKV model, and EKV model basically looks into the MOSFET operation exactly as the other ones. However, rather than considering source as the reference, it uses the bulk as a reference, right. So, with respect to bulk, everything has been taken care of. So, we will not go into details of all these models, this will require a separate coursework to actually do it. So, let me come to the other model, and this is basically the EKV model. And the difference between the EKV and the other model is that the EKV model, rather than source, it takes the bulk as a reference, right, for all voltages. So, it is basically with respect to bulk, gate to bulk, source to bulk, drain to bulk, which we are taking, and this is quite an interesting model. However, we will not be going into details of EKV because it requires a very other sort of single lecture will not be sufficient for doing it. So, let me recapitulate what we did in this lecture. We looked into level 1, level 2 and level 3 models, its relative advantages, and we also looked into relative disadvantages, and we also saw that level 1 was purely analytical in nature. However, level 2 and level 3 were analytical plus it was empirical in nature. Both were added in case of level 2 and level 3, and we saw its relative merits and demerits. There was a problem of discontinuity in level 2 and level 3, and therefore, people went ahead with higher level models. We did not go into details of other models, for example, EKV or BSIM. There are very good books available on that, there are very good lecture series available on that, you can have a look into that. And next time when we meet, we will take up some valid logical examples on SPICE and show it to you how the characteristics are drawn. With this, let me thank you for your patient hearing, and we will meet next time. Till then, bye.